Good morning, students. Today we are going to take a short revision of the complete chapter Real Number, Standard 10, CBSE Exam 2025. Number system is the name of the unit, and this chapter having the contribution 6 marks. Chapter 1 Real Number. So let's have a quick revision. Real number. In real number chapter, these are the all points we have to cover today. Rational, irrational numbers. In rational numbers, we'll discuss terminating, non-terminating, recurring numbers. Then we'll discuss about factor theorem. Then fundamental theorem of arithmetic, prime, co-prime and composite numbers. Then we'll discuss about SCF and LCM and the property related to SCF and LCM. Any positive integer ending with 0 property. Any number ending with 0 with the power n. Prime number theorem, then proof by contradiction, and then last we'll discuss about the words problem. So let's start with the rational and irrational number. So what is the rational number? A number which can be expressed in the form of P upon Q, where Q is not equal to 0 is called as a rational number. And the number which cannot be expressed in the form of P upon Q is called irrational number. For example, 3 upon 5. We can say this is a rational, while root 2, root 3, etc. are irrational number. In rational numbers, terminating and non-terminating and recurring numbers are included. Now, what is the terminating? A number whose denominator can be expressed in the form of 2 raised to and 5 raised to power. Suppose 3 upon 20. So 3, 20 we can write it 4 5s are 20. And what is 4? 4 is the power of 2 and 5 is to 1. So whenever any number in denominator form can be expressed in terms of 2 raised to m, 5 raised to n, then the number is called terminating. What about the non-terminating and recurring? Suppose we are consider this example 10 upon 3. So division is 3.333 and continue. So a group of number or a number that repeat again and again is called non-terminating and recurring. So these two types are there in a rational number. Let's move for the first theorem, fundamental theorem of arithmetic. What is the fundamental theorem of arithmetic? In this theorem, there is a composite number. Now first we'll discuss about what is the composite number, prime, co-prime numbers. So all of you well known, prime numbers that is 2, 3, 5. A number whose 1 is the only factor. 2 ones are 2, 3 ones are 3, and other than 1 there is a no factor for the particular number is called prime number. Now what about the co-prime? Suppose 2 is there and 3 is there. 2 into 1, 3 into 1. So these two numbers have only one common factor, that is 1. So this 2 and 3 is called co-prime. Suppose 3 and 5, these are also co-prime. 13 and 5 are co-prime because there is no common factor other than 1. Therefore, they are called as a co-prime. Now, this co-prime word is very, very important while proving the theorem. Let's move for the next topic, that is co-prime, prime and composite. What is the composite number? A number which can be divided by itself also, 1 also, and other than that there is a more factor, that is 5, 5s are 25, so it can be divided by 5 also. So this 25 is called as a composite number. One more example we can take. Suppose 9 we are taking. So 9, 3 3s are 9. So here 9 can be divided by 9, 9 can be divided by 1, and this 9 can be divided by 3 also. So this is another factor than 1 and itself. Then such a number is called as a composite number. Now, what is the fundamental theorem of arithmetic? So, fundamental theorem of arithmetic is based on composite number. For every composite number or every composite number can be expressed or factorized in the form of primes. For example, if we take 35, so 35 is a composite number. Now, why it is composite number? Let's again revise. 35 can be divided by 35. Yes. 35 can be divided by 1. Yes. And you know 7 5s are 35. So 35 is divided by 7 also, and 35 is divided by 5 also. That's why 35 is a composite number. Now this composite number can be expressed in the form of primes. It is 1 into 5 into 7. So 5 into 7 into 1. So product of the primes, that is 5 into 7. Now their order is not important. The way they occur, the order is not important. We can write 7 into 5 or 5 into 7. So every composite number can be expressed as a product of its prime irrespective of the order of the product. 5 into 7 or 7 into 5. So this is called fundamental theorem of arithmetic. Now, what is the use of this fundamental theorem of arithmetic? So it is useful for finding the SCF and LCM of numbers. Now, let's go for the SCF and LCM. So what is SCF? The long form, all of you are well known. SCF is the highest common factor, while the LCM is the least common multiplier, you can say. Okay. Here SCF and LCM. So SCF, LCM. For SCF and LCM, there is a very common rule and which is very useful also. The rule is what? We have to factorize the given numbers in prime factor form. If we find all the prime factors, then we have to take the smallest power of common prime. Smallest power of common prime, and while LCM we have to take the largest power largest power of each prime. This prime word is very important. We have to find first prime, and then if we take the common number and its smallest power, then it is called SCF. If we take the prime factors, all prime factors we have to consider and their largest power, then the product is LCM. Let's take the example. Suppose here 35, 20. 35. So let's express this in the form of primes. 7 into 5. 2 into 2 into 5. In the form of powers, we can write it 2 to the power 2, 5 to the power 1. Here in these two numbers, this is the expression of the number in terms of prime. For SCF, we have to find the smallest power of common primes. So which one is common here? The common is 5. And what is the smallest power? So here is only 1. Now let's go for the LCM. What is LCM? LCM is each prime. We have to take all the primes in factorization. So 2 is here, 5 is here, 7 is here. Now while taking the each prime, we have to take their largest power. So largest power here 2, largest power is 2, 5, largest power is 1, 7, largest power is 1. If we multiply these all, we'll get LCM of these two numbers. So 4 into 5 into 7, 20 into 7, that is 140 is the LCM. Again, we'll revise. What is SCF? SCF is the smallest power of common prime. What is LCM? LCM is the largest power of each prime. All the numbers we have to take as a prime factors and their largest power. While in SCF, we have to take the common one and the lowest or smallest power. That's all. Now, let's move for the next theorem. Any positive integer ending with 0, any positive integer ending with 0 is divisible by 5. Suppose here 20. You can say 2 into 2 into 5. If we take 70, again 7 into 5 into 2. So you can see every time whenever any number ending with 0, 5 is a common factor for them. So this is a theorem, very important one. Any positive integer ending with 0 is divisible by 5. Divisible means it's one of the factor must be 5. So related to this, there is a proof. Check 6 raised to n can be n with the digit 0 for any natural number n. Okay. So 6 raised to n natural number means it may be 2, 3, 4, 5, 7, any number, 1000, 12,000, any number we can take. So when it will end with 0, when one of the factor of this term is a 5, like this, 20 end with 0, so 5 is a factor, 70 end with 0, 5 is a factor. Here if we found the primes of 6, there are 3 into 2. but there is no 5 as a factor. If 5 is not a common factor for 6 or it's a prime factor, then it can never end with 0. Now we have to explain only this term like this. 6 raised to n, its prime factors are 3 into 2. 5 is not a prime factor of 6, therefore it can never end with 0 for any natural number n. That's all. This may be asked for 2 marks. Now let's move for the next one. The next useful theorem. You can say it is a property. P be a prime. Suppose P be a prime number, A be a positive integer, A be a positive integer, if P divides A square, if P divides A square, then this P divides A also. If P divides A square, then P divides A also. This is a very, very important concept. Now let's see with example. Suppose here we are taking 16. If 16 is divisible by 2, see this, P is a prime. So whatever the division number, it is a prime number. A is an positive integer. So it is a 16. So 16 is divisible by 2. Yes, 2 8s are 16. Now take the square root of 16. What is the square root of 16? Square root of 16 is 4. And it is still divided by 2. 2 2s are 4. This is our A and this one is P. So A square, this is A square term and this is square root of the term. So the theorem is that P be a prime, A be a positive integer. If P divides A square, then P divides A also. So this theorem is useful for proving root 2, root 3, root 5, root 7 is an irrational number. We make use of this theorem for proving this theorem for 3 marks. So let's prove the theorem in detail now. In exam it is asked that this proof is called as the proof by contradiction. Now prove that root 2 is an irrational number. Prove that root 2 is an irrational. So for this proof we'll use the method of contradiction. Proof by contradiction. Now what is contradiction? So let's see. Let assume root 2 is a rational. We consider that root 2 is rational. We have to prove that root 2 is irrational, but with this time we are taking it root 2 as a rational. And if it is a rational, come to the first definition. What was the rational? A rational number which can be expressed in the form of P upon Q, where Q is not equal to 0, and in simplest form they are co-prime. So here if it is a rational number, so root 2 can be expressed in the form of A upon B, where A, B are co-prime. Now what is the co-prime? Again come to the basic definition. Co-prime, a number whose common factor, numbers whose common factor is only 1. There is no other common factor than 1. These two have only one common factor, and that is 1. So root 2 is a rational means it must be in the simplest form A upon B. A, B are co-prime. No other factor than 1. No other factor than 1. So root 2 A upon B, A, B are co-prime, no other factor than 1. Squaring both sides. It's squaring both sides. If we take the square of both sides, it becomes 2. This A square upon B square. If we rearrange this, 2B square is equals to A square. Now A square is a product of 2 and B square. It means A square is divisible. A square is divisible by 2. And according to the theorem, which theorem? P be a prime, A be a positive integer. If P divides A square, then P divides A. It means 2 divides A square, means A is divisible by 2 also. According to this theorem, if 2 divides A square, then 2 divides A also. So, we can express A as 2 into C, because 2 divides A, means 2 is a multiple of A. So what is C? C is a sum prime. We can say sum prime integer. Sum prime integer. Now put this in equation 1. Which is our equation 1? This is our equation 1. So 2b square equals to A square. 2b square equals to A square. In place of A, we substitute 2c. If we square it, 4c square, 2 2s are. So b square equals to 2c square. Again, we got that 2 divides b square. B square is divisible by 2. Again, according to theorem. Which theorem? If P is a prime, A is a positive integer, P divides A square, then P divides A. So here B square is divisible by 2, therefore B is also divisible by 2. So what conclusion we got? Here A is divisible by 2 and B is also divisible by 2. Means A, B both are divisible. Both are divisible by 2. But we assume that A and B are co-prime. And what is co-prime? No other factor than 1. But here, other than 1, there is a 2 is one of the factor. So whenever we prove that root 2 is a irrational, 2 will be the common factor. If we prove root 5 is a irrational, 5 will be the common factor. If we prove root 7 is a irrational, then 7 will be divisible to both. So in this way, A, B both are divisible by 2. Our assumption that A and B are co-prime is not correct. So why this contradiction arises? Because of our incorrect assumption. So at last we'll write down that because of our incorrect assumption, what was the incorrect assumption? Root 2 is rational. Root 2 is rational. Therefore, we conclude that root 2 is a rational. If it is rational, then it must be in the simplest form, a upon b, and a upon b, and a and b must be co-prime. But here a and b are not co-prime. Our assumption is incorrect. Therefore, root 2 is a rational. This statement is incorrect. Root 2 is a rational. So it proves root 2 is irrational. In this way, we can prove root 3, root 5, root 7. We have to replace only in place of 2. If we replace it, if we replace 2 by 3, the whole proof will convert for 3. Everywhere, wherever root 2 is there, so it becomes 3, root 3 square, 3, then 3. Everywhere it will be replaced by 3. If we have to prove root 5 is irrational, just replace 2 by 5. If we have to prove root 7 is irrational, we can replace 2 by 7. So in this theorem, these few points which are very important, a and b are co-prime. What is the meaning of co-prime? And the second important theorem, a square is divisible by 2, then a is divisible by 2. So this is the proof for root 2, root 3, root 5, root 7, etc. is an irrational number. Now co-theorems related to this are 3 plus 2 root 5, or 5 minus root 3, or 1 by root 2, or 3 root 2 is irrational. This also may be asked. So let's discuss about the next theorem. Look here. Next theorem. Prove that 3 plus 2 root 5 is a irrational. So again, we'll prove this by contradiction method. So let assume it is a rational. Now, if it is a rational, it can be expressed in the form of a upon b. What is a upon b? It is the simplest form of the rational number. And what are the a and b? A, b are co-prime. Now again, what are the co-prime? They have only one as a common factor. A and b are integers. Now this time will not prove in detail. This plus 3 on the right hand side, it becomes minus 3. If we take the LCM, then root 5 equals to a minus 3b upon 2b. Now pay attention here. A, b, 3, 2, these are integers. These are the integers. And in the rational form. These are the rational form. This is rational. While the left hand side is root 5, which is irrational. So rational and irrational cannot be equal. So our assumption is incorrect that 3 plus 2 root 5 is a rational number. So we'll write down 3 plus 2 root 5 is an irrational. In this way, for 2 marks, we have to prove this one as a irrational number. Let's discuss the last part of the real number, that is few word problem. What happens in word problem? Many students are not able to understand about the SCF or LCM. In the given question, we have to find SCF or LCM. So let's take few examples of the word problem. So one word problem I am taking. There is a circular path. There is a circular path around a sports field. A sports field is there, a circular path. Sonia takes 18 minutes to drive one round of the field, while Ravi takes 12 minutes. Sonia takes 18 minutes to drive one round of the field, and Ravi takes 12 minutes for the same direction and they start same point. Ravi takes 12 minutes for the same. Suppose both start at the same point. Suppose both start at the same time in the same direction. After how many times will they meet again at the starting point? Again will meet at the starting point. This is Sonia and Ravi start moving along a circular field. Sonia needs 18 minutes to complete round. Ravi needs 12 minutes to complete round. So in this case, we have to find LCM. Whenever there is a word again at the same point or at the starting point, we have to take the LCM. Whenever there is a common form, then we have to take the LCM. So 18 and 12, the LCM of 18 and 12. Again, we'll take the example. What is the LCM and SCF? First, we have to find the prime factors. So prime 2, 2 3s are 6, 6 3s are 18. Now 2, 2 2s are 4, 4 3s are 12. So 18 in the form of power 2 and 3 to the power 2, while 12, 2 and 3 to the power 1. Now we have to find LCM. So what is the shortcut for LCM? The shortcut for LCM is largest of each prime, largest power of each prime. So largest power of each. Each means every number we have to consider. Here 2 is there, then 3 is there. Anyone? No. So what is the largest power? Here power is 1, here power is 2. So we have to take the largest power. Here power is 1, power is 2. So we have to take the largest power. So 2 square 4, 3 square 9, 9 4s are 36 minutes. So after 36 minutes, they will meet again at the starting point from where they started. So this type of question may be there. One more example we'll consider. 3 alarm clocks ring their alarms at regular interval of 20 minutes, 25 minutes and 30 minutes. I repeat, 3 alarm clocks alarm at regular interval of 20 minutes, 25 minutes and 30 minutes. Now what is the question? Respectively, if first beep together at 12 noon, at 12 noon the first beep together. If first beep together at 12 noon, at what time will the beep again for the first time? Again, all the 3 alarm again at the same time will beep after 12. So again there is a common one, and when there is a common, we have to take LCM of these three. So LCM again, if we want to find the LCM, we have to find the primes. So 2, 20, 25 and 30. What are the prime factors of 20? That is 2 square 5 power 1. 25 5 power 2. 30 5 3 into 5 into 2. Now we have to take the LCM. LCM means what? Largest power of each. Each means the numbers are there. Each number. So which number is there? 2 is there, 3 is there, 5 is there. So what is the largest power of 2? Here is 1. Here is 2. So largest power is 2. Here largest power 1. Yes, 1. 5 largest power 2. So for 2 square is 4. 3 5 square is 25. 25 4 is 100. 100 3 is 300 minutes. And what about 300 minutes? 300 minutes, if we divide by 60, it becomes R. So 6 5s are 30 after 5 hours. So after 12 noon means 5 hours after 5. So 5 p.m. they will be again. Let's take one example of the SCF also. So these are the examples of whenever there is a again at the same time at the starting point, at that time we have to find the LCM. Now teacher have to arrange all the student of standard 8, 9th and 10th in a auditorium. In a single hall we can say. There are 84 students of standard 8. How many students? 84 students of standard 8. 8th standard, 9th standard and 10th standard. So there are 84 students of standard 8, 63 students of standard 9 and 42 students of standard 10. And teacher have to arrange these students in a common hall. The condition is that each class student must be in the same row. Same row means number of rows may be different, but 9th and 10th and 8th will not mix up with each other's row. Teachers have to arrange all the students of class 8, 9th and 10th in a single hall. There are 84 students of 8th standard, 63 of 9th and 42 students of 10th standard. Find the minimum number of rows. Find the minimum number of rows in which same class students can be arranged. Find the minimum number of rows in which same class students can be arranged. Now as there is a minimum word, student go for LCM. And this is the wrong one. Minimum means common for all. And what is the common for all? Common means SCF. Minimum number of rows means common from all. So we have to find SCF. SCF of these three numbers. So 84, 63 and 42. Giving you 1 minute. Come on, find the SCF of 84, 63 and 21. Solve it. You will get as a SCF as 21. So as we get the 21 as a SCF, so how many rows are there? So let's count the rows. 8th standard, there are 84 students, and in each row, how many students are there? 21. So how many rows will be there? 21 4s are. So we have to find division. So 4. 9th standard, how many students are there? 63. And each row, how many students are there? 21. So there will be 3 rows of the 9th standard. And what about 10? 42. So 42 upon 21, that is 2 rows of the 10th standard. And total rows will be 4 plus 3, 7 plus 2, 9 rows. In 9 rows, all the students of 8th, 9th and 10th can be arranged separately. That's all. So in this way, we can revise the chapter rational number. Thank you.